doing this, please check that your computers are working properly, because the technicians told me that they were fixing the computers in the last week, and hopefully everything will be working all right. If something does not work, please leave a note so that when they come this week, they finish fixing everything. Remember that the password for the computers is alumno, and hopefully all the computers will be updated, and Stata 14 is working now in all the machines, so hopefully everything will be fine. Maybe if there is something, just leave a note, like in previous. Please notice that someone uploaded the Xiao book in the Google Drive, so you may want to download it if you want, and keep it for your own individual use. I'm passing several books about panel data that you may want to look at. They are useful. So I have versions 2 and 3 of Xiao, and others are by Arellano and Baltaghi and Woolrich. So you have those books that you may want to look at. It may be nice to look at the table of contents, because you will see that most of what we are going to do is common to all the books. So this is standard program. Do you have any questions before starting? Anything that you may want to look at or see? Okay, so now let's revise something that we were doing at the end of the previous class. At the end of the previous class, I was talking about chapter 2. Chapter 2 is about heterogeneity, how to deal with heterogeneity. And I told you something about one of the F-tests, but I'm going to repeat now something similar with this F-test, which is the one that is printed in Stata by default, and is the one which is more typical. Okay, so I'm going to finish now this part of the F-test, which is the most typical F-test. This F-test here. I'm going to talk about the heterogeneity, and the heterogeneity that is the most typical one. It's deciding whether a pool model, which is the one that you have up here, a pool model is enough, or it is necessary to use a different constant model. So this is the pool model, this is the different constant model. And the idea here is to decide whether to use the pool model, or we need to use the different constant. Typically, in all the applications that we have seen, we have to use the different constants. So this is the typical outcome. So, but still, it may be useful to look at the possibility of using just the pool model. So the idea is, if the two models are more or less the same, so you could use the pool model, the sum square residuals would be about the same. In S3, the sum square residual of the pool model, S2, sum square residuals of the different constant model. Now, and the null hypothesis would be that the constants are the same. The alternative is that the constants are different. So the null is this, the alternative is this. Do you have any questions about this? This is similar to what we saw in the last class, but special case which is very common. So the idea is, if you have heterogeneity, then the sum square residuals are not the same. The lower one would be smaller. If you don't have heterogeneity, sum square residuals would be approximately the same, and you would have to use the pool model. Now, if you come to this F that we see here for testing the null hypothesis of homogeneity, then you see here what we do. We do the same as in the previous class. We compare the sum square residuals. If they are about the same, then this difference is small. So the F test would be what? Big or small? If they are about the same, S3 and S2. Small or big?
Small close to zero.
Small. Okay, so in this case, if under the null hypothesis, this should be small. But we don't know how small is small. So we have to somehow make justice and divide, take the average, or dividing by the n minus 1. N minus 1 is the number of restrictions that convert the alternative hypothesis into the null. N minus 1 is the number of restrictions. So this number of restrictions is n minus 1 because in the unrestricted model we use capital N constants, and in the restricted model we use 1. So the difference, n minus 1. Okay? So this is the numerator of the F test. Do you have any questions about the numerator? It's just the mean difference of sum square. Now, we don't know the distribution of this numerator, so that's why we have to normalize it. We have to normalize it, dividing it by something that is comparable to the upper part. And this something that is comparable to the upper part is the variance of the unrestricted model. This is the sum square residuals of the unrestricted model and divided over the number of degrees of freedom. Why is this the number of degrees of freedom? Why is this and not some other quantity? Why this? Anybody? Why this number? Why n times t minus 1 minus k? Some help here? So I told you that this is the number of degrees of freedom of the unrestricted model. You have to know that the number of degrees of freedom is always the number of total observations minus the number of total parameters that we want to estimate. So the number of total observations is n times t. No? We are assuming that we have a complete data set. N times t. Then n is the number of constants, and k, capital K, is the number of slopes. Okay? So nt is the number of observations, n is the number of constants, and k the number of slopes. So that's why we have this number. Okay? Do you have any problems with this? So the good thing about this statistic is that we know the distribution under the null, and the distribution is an f with n minus 1 degrees of freedom in the numerator and nt minus 1 minus k in the denominator. So this is a standard distribution, standard f, that you can look up in the f of Fresnel tables. It's easy to understand, and it's already programmed in Stata. So in Stata you don't have to remember the number of degrees of freedom or the number of critical number. but you can just go ahead and look at the p-value. The p-value is printed in the f-test, and it is very easy to look at. If the p-value is very small, then what do? We reject or don't reject. If the p-value is small,
Reject.
we reject. No? And if it is large,
We accept.
we do not
We
reject.
don't.
No, accept,
don't
that word, like you have never pronounced that
Yeah.
word here. We have never heard that. So the idea here is that you can decide for yourself whether to reject the null or don't reject the null. If the if you have a p-value which is small, small means smaller than the number that you choose. Typically you choose 0.05 or 0.01. If one has a large data set, usually you would choose 0.01 because 0.05 is a very it's not very conservative. 0.01 is much more conservative and much more demanding. Do you have any questions about this? This is the same as in the end of the last class, but applied to this particular case. This is the particular case in which is printed in the output of data and which is useful in this case.
Question. If I run a regression with fixed effect and the f value is large,
The f value is large. Okay.
It means that.
But which f value? Because there are
the
several
f
values in the output. Which one?
The overall f test for the regression.
No, then we are not talking about that.
Ah, okay.
No. We are talking only about testing the heterogeneity.
Okay.
And I think that you're talking about the f-test for testing about the joint significance of all the slopes.
Ah, okay, yeah.
Something different. So we will look at this in the example. You know that f-test can be used for many things, and that's a different use. No. So let's go back. So now, what I would like you to do is to go back to the example that we are using, the wage pan example, and get the data that you were working with in the last class. Remember that in the last class I told you that we could not save anything, and moreover we had a problem because we tried to estimate some parameters and we couldn't. Okay, so we go back to that situation and see what we can do. Do you have?
Well, I missed the last class. I didn't come,
Okay.
so I'm a bit lost.
So now, what I want you to do is you go to the Google Drive. You know about the Google Drive? No? Tell him. the Google Drive.
Yes.
So we
You just
have a
have to-
Google Drive that
To go to
we
this
share.
website, you can Google the name of the professor,
I can't even turn this thing on.
and it's down there. You have to turn on down there.
No, thank you.
Okay, there you go. It's getting. No signal. Nice.
So I told you that we were going to use
The
the
one,
example
or it is
called
one,
wage pan. Wage pan.
or it,
Sí, no puede que no esté.
No, en algún sitio hay que encenderlo. Pero yo
Ah, no, joder.
no sé.
y si no el otro.
Yo creo que sí, creo que es un problema tan fácil como eso. On off.
So please go to the example which is called wage pan, and then in the wage pan, please open it. Make sure that you're using Stata 14. Do we have a Stata 14 in the machines around here? But the technicians told me that they have Stata 14 also. No? Okay, so now you see that Angel here is opening the data set, and we have to remember that we were trying to do to estimate a model about wages panel, and that the model was very easy to do, very easy to estimate, but we had problems. The first problem is that you need to save your output, because if you don't save your output, you're dead, because you spend time working and then you have no output. So it is very important to save the output. Here in Stata, saving the output is very easy. What you need to do is use a do file. A do file, you can here you can get it there. How new do file editor, and this new do file editor is a text editor in which you essentially save the commands that you're using. You save the commands, but there are two big qualifications. First, you only save successful commands, no? Because if you save all the garbage, you're wasting your time. So maybe you are working in an afternoon, and how many successful commands can you usually get in an afternoon? Maybe 4 hours. How many successful commands? How many would you get? No, maybe 15. Maybe 15. But not 200. Not 200. Maybe 14, 15. That's a good output for a whole afternoon. Now, if you're working for maybe 15 days, 20 days in a data set, maybe you end up with 200 successful commands. That's a lot. That's a lot of work. A lot of output. And essentially, everything that you do has to be saved in the do file. Save all the successful commands. How do you save them? Cut and paste, cut and paste. No big deal, cut and paste. But you have to save them commented. So you have to make comments to yourself or to any other person, and make sure that you say there what you're doing and why. Because what happens if you look at your own data set a month from now? What happens? That you don't understand anything. You forgot. Everything. So it is necessary to write down what you're doing, why you're doing it, and those are called comments. Those are not successful comments. Those are comments. Okay? So it is very important to just write down what you're doing, why you're doing it, and then keeping the successful commands. As I say, it's just a matter of cut and paste. So you don't have to do weird things, cut and paste. You don't have to rewrite anything. Remember that I told you that if we have several windows in Stata, I'm going to go through that again. Several windows. One big window is about results. The results of the estimation or whatever you're doing, graphs or anything, come out here in this main window. This is the output result, the window. Then you have this other window, which is the variables window, and see that you're working with the 9. Then we go to the 14. Because in the 14, the variable window is on the right hand side, so that you can tell what it is. So the variable window is going to tell you what variables are available, what is the explanation for those variables, and it's going to help you use the variables. It is important to know what variables you have and what they mean. Then there is another window which is called the review window. I call it the recycle window because the recycle window is going to help you a lot by not having to type everything again, but just clicking on the things that you have already used, and then maybe you want to modify them. So the recycle window or the review window is very important because all the input that you type in is going to appear here in the review window. And then I want to remind you that there is a fourth window down here, which is the command window. The command window. In that window, every time you do something in the command window, that causes something in the output window. Important to know about those four windows. Then, if we are talking about what you do in the first few classes, you don't use the command window. Just forget about the command window for the moment, and you would use the fold down menus that you have in the upper part. For instance, if you click there in the statistics and you go to panel data here, and then you go to this, setup and utilities. So you have a lot of options there to be able to deal with the type of data that you may have, in this case, panel data. So typically what you want to do is use this type of fold down menu to be able to do things. Even the simple things that we are going to do now, we should use them through the fold down menus because it is much easier and much more flexible. So let's go now to the to where we ended in the last class. The last class we arrived to statistics, up here in the statistics, and then longitudinal panel data, linear models, and then linear regression. So we were here in this window, and in this window what we did was to use the wage pan. The dependent variable was L wage, remember, logarithm of wage, that was the dependent variable. So you can choose it from the menu that appears there. It is almost at the end. And then, does anybody have the variables that we use?
En descargas.
Black, express,
Black.
is, education, junior, variant, soul, and hours.
Otra
So
vez.
for the moment,
Me quedo con black.
Black, experience,
Experience. Experience.
is
Es como está.
Hispanic.
Hispanic.
Expert. Okay.
Union. Mario.
Sí, lo que pasa es que tienes que abrir,
With two
abrir
M's.
el
Mario.
pero
Yes.
Yo estaba aquí y pinchaba aquí lo puedo simplemente lo puedo
South.
So,
And that's all.
perfect.
Sí,
Okay.
tienes que hacer lo mismo que era
Se hacía algo aquí para empezar, ¿no?
No, 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 no.
Sorry, an hours.
Tienes que hacer statistics. Y luego panel longitudinal, panel data.
That's it.
Y luego linear model.
Okay.
Y aquí el primero. Y ahora ya estás aquí. Bueno, donde estaba es ahora. Sí. No, pero ahora no es así.
Ahora vamos a repetirlo.
But we made a fixed effect.
Yeah, so we wanted to estimate this precise model, but using the simplest model that we are going to work with, which is the fixed effect. Fixed effect model, which is estimated by ordinary least squares. So here you can either come to the OK and then continue, or you can go and recycle. You can go and recycle. If you leave there, you put FE.
You have to choose linear.
Instead of the R, you put an F, FE,
First row.
and then FE, and then click, and then you get the estimation. So this is the simplest estimation that we are going to see. This is the fixed effect model estimated by ordinary least squares, or the same, it's dummy variable least
Here
squares.
you can
Dummy
select
variable
the
least
variable.
So we are estimating the model
This is
using ordinary least squares. There's nothing very sophisticated. It's just a simple model, simple linear regression model, and we estimated using ordinary least squares.
O sea, pasado hasta elegir linear regression, bla, 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 y entonces va aquí. Pero de aquí hay una...
If you remember, we arrived at this situation. So what I would like you to do now, instead of looking at the output, I would like you to do edit the do file. Go to the do file and put what you want to put. You want to make some comments, do some things that you may want to do in the do file. You may just want to cut and paste the output, the input. I'm sorry. Cut and paste. So you can use just one line to cut and paste and make sure that you have a do file that is beginning to grow. You have to remember, I told you, that you have to use comments. And how do you use comments in the do file? Anybody know?
Is that bar and asterisk? I don't know how to say.
Asterisk.
Asterisk.
So you can use a bar and asterisk, or you can use asterisk already. Only. Asterisk only is good enough. Si te quedas aquí con lo que sea, ponte ahí con algún...
Aunque sea en papel, aunque sea en papel,
Ah, es que no lo tengo aquí. No lo tengo. Es un trabajo que empezamos a hacer otro día. Luego hablamos. Okay, so the question is that we have to try to explain the logarithm of wage of a sample of males in the United States. And what we're going to do is to try to find some variables that are useful for explaining the logarithm of wage. And some of the variables, we have them already there. some of the variables are like the being black or not being black, being Hispanic or not, the labor experience, and also the number of hours worked, and some other and union. And the important variable is union, because we have to find out whether being unionized is important and affects wage upwards. So that's the
Can I just ask very quickly, why the logarithm of wage and not wage?
because in this literature, a lot of research have found that logarithm is more appropriate than the linear. So, I mean, after time, people learn things. One of these, this one.
Okay.
But of course, you can use just the level, because the level is already there, and you can just try if you want. So there's nothing is compulsory. It's just that he has been learning. We have been learning by doing it for some time.
¿Me puedes
Okay,
repetir
so-
las variables, por favor?
Now, I would like you
Like to
to
write
define a do file. Please save the do file. So you have a do file with some comments. You have to use asterisk in front of the line of comments, and so that you have maybe 2 or 3 lines of comments, and
So-
then the estimation.
De su-
The estimation.
Gracias.
Now, I told you now how to save the do file and be able to save all your work. Notice that all your work can be synthesized in maybe a couple of pages. A couple of pages is all the output that you get after weeks of work. And the do file is very useful because it can be transferred from one computer to another, from one version of data to another, and it's going to be very useful for working with other co-authors everywhere. So now put a comment also, so that we can see a comment would be before, in the line before that. You put a asterisk and then comment, whatever comes.
¿Debería estar? ¿Debería estar aquí?
No. Do file. Okay, so now what I would like you to do is to do something else. We want to get some graphs, because graphs are very important. It is very important to notice whether you have an apparent relationship or not. So let's do some graphs. The first graph would be logarithm of wage. That would be the vertical axis. And then in the horizontal axis, you can use, for instance, education. Try to find out if there is a positive relationship between education and logarithm of wage. So it is important that you do this through the drop-down menu. The drop-down menu is very important. You just use If you don't know what to use, what would you use? The most sophisticated or the simple? Simple. So let's find a simple way. So there is one simple way there that tells you create graphs, and the create graphs is not that easy to use, but it is extremely useful. Because those graphs, you want to save them, you want to manipulate them, you want to put one on top of the other, you want to activate, deactivate, you want to do a lot of things. You need flexibility to work with the graphs. So it's not just doing a graph, it's flexibility for doing the graphs, for saving the graphs, for everything. You can use the line graphs for panel data, or you can use any other. Let's see. I want you to look at this. This is the box, the general box for graphs. And this is not specific for panel data. But it is very useful because here you can, you see this is important because it says this definition of graph, and the main idea is now you go to create, and then once you create a graph, it asks you which is the y variable, the x variable, so you can choose from here LWH and then education, for instance, so that we can see what is the relationship between education and LWH. Now it takes some time to do the graph. And see, this is the type of graph that we get. It looks a little weird because it is like a fish. But sometimes it is a helpful tool. In this case, what would be the relationship between education and logarithm of weight? This, like this, like this, like this. What is the relationship? Do you know? It is hard to tell by just looking, no? Yeah. The eyeball test is not working very well in this data. This data has a lot of problems, so don't think that this is simple. It has a lot of problems. So now, since we don't see anything there, what do we do? A line, no? Yeah. We like at least a line. You're not meaning a straight line, but line. Okay? No, we never say straight. We say line. Okay? Straight. Because straight is very limited. Very limited. Okay, so let's see if we can get some lines that help us with this. I need help. I need help. I need you to tell me how to do it. So you have to look into it. It is easy. Try to find what is the way in which a line can be drawn. Well, it may be a regression line, maybe a non-regression, kernel, non-parametric, whatever. So in general, you would think of non-parametric lines, because parametric lines are very limited. So because you may have something like this, and you draw a straight line, you lose the information. How many weird graphics can you get like this one? Like 25,000. No? So we need something that doesn't look weird. We need something useful. So just try, because it's not so difficult. Just try. And remember that you have the fold down menus. So you go to the fold down menu and try to find something that does the trick. No? We did some trick.
In the menu within the graph window, right?
Yeah, in the graph window. The fold down menu of the graph.
Yes, but yes, we can.
Yo creo que no tengo los datos de base, porque estoy en el correcto, pero no me sale ningún gráfico. Yo creo que he hecho el camino correcto, seguro que no, pero he llegado hasta aquí, pero no se parece a lo tuyo, no tengo ese tablet. Con lo cual, al no hacer...
Cualquier cosa menos que...
Sí, esto sí, pero no, estos datos están bien, sí, no tenía que llevar previamente. ¿Sí? Esto lo que hago en momento, two-way graph, y al poner aquí y-axis y x-axis, the wage y el wage. Y entonces, vale, olvida por line, las catas que tú tenías, sí. O sea que sí que tengo los datos.
Entonces, estás hablando con otra versión de la que selecciona el logaritmo del aquí y aquí con, por ejemplo, la ecuación del producto. Está por ahí, pero y dale OK para ver qué te sale. Entonces está pensando y ya te sale ese.
Ay, yo estoy como tú, joder.
Pero el problema siempre es que estás con otra versión, entonces no ves exactamente.
¿Y todos los demás están con la misma versión?
Depende. Estás con la 9 también, ¿no? Are you?
Yeah, can I
Are you with the?
Yeah, because we are in version, we have the same problem. Look how you can tell what is like this, not,
Yeah, that's
it's
just-
not like this. Why?
Exactly, that's just about the version, because of the versions. You have to open first the Stata 14.
Yeah,
You can close down this. Exactly.
same or not?
Don't say. You can repeat it because it's not so long. So open first Stata 14 and then
Yeah.
open the file. Open
But
the.
this is Spanish. I know Spanish.
You don't speak Spanish, but it's quite easy to understand because they are not more. They are not quite different, and it's the same menu that you're going to see in on the board. Or you can try to use the older version, as you see, because but the problem is the older version is gonna show you
So
different
please
menus.
notice there is a
For
variety
example,
of
how we could choose, for
possibilities.
example, this is 14.
If you go to
Yeah.
non-parametrics
In order to
and use
open,
something called like kernel
first you
or
can open the
lowest,
file.
so let me
through
write
this,
down what that is so that
through
you
this menu,
can
or
search
directly
for
you
those
go to the
possibilities. Lowest,
We download the file.
exactly. And you can just these ones, just in this section, and you have already opened the file here.
so if you look at these
Then you just follow
possibilities,
the instructions.
you will find something non-parametric adjustment. But notice that you are not prohibited from using the help. Okay, the help can be used. No prohibition. So you can use the help because the help is going to be very useful. If you can even use Google. You put Google lowest data, and then it will help you. So please notice that there is a lot of help. You will not have me all the time for the rest of your life. But you will have Google and the help of Stata that you can look at. So please open your mind to those possibilities. It is very important. The help in Stata is not very easy to look at, but it is very useful if you sit at it. So look in the help of Stata and see that you have a lot of possibilities. If you look at help kernel or help lowest, that words that I wrote there, you will be able to find a lot of things that are helpful for you.
Hay versiones de Stata, bueno, las versiones de Stata están en español,
Sí,
entonces hay varios que no,
las más
varias personas que no
modernas
hablan,
están en español.
que no hablan
Esa,
eso, claro, no hay forma.
o sea, las más antiguas están en inglés.
La versión 9 está en inglés. Justo.
Exacto, pero la 14 está.
Y están ahora instaladas tanto la 9 como la
Ah,
14.
sí, sí. Que está bien, para lo que pasa es que no se puede liar.
Sí, porque seguir se sigue, pero cuesta un poquito más.
Busca lo de kernel.
El kernel, vale.
Y el lowest, ¿no? Lo hicimos una vez lowest.
Sí, es verdad. Vamos a ver más.
Búscalo para que ellos lo vean. Que se animen.
¿Estará en el panel, en otro panel? No.
No.
Entonces están gráficas estadísticas.
So anybody found lowest in the health? It cannot possibly be very difficult because it's there. So the idea is getting a non-parametric regression in which you allow for non-linearity, but not smooth non-linearity. You may have kinky non-linearity. You go to help in the upper part. So notice that the important thing in this class is that you do the thing, not me. I know how to do it, but I will not tell you unless you have to find it for yourself. Because if you don't find it for yourself, it doesn't help.
Es que me perdí antes de clase, estoy aquí más perdido.
Son estos dependientes y luego tienes black, gris, is de hispano, ¿no? Son metodogramias. Todo education, union, science y artes. La primera es la dependiente.
Este es el lowest.
El lowest, sí, pero te cuenta que estás poniendo personal identifier que no tiene sentido. Y aquí el low wage está bien. Necesitas poner education.
Porque no se ve.
You see that Angel is now close to the solution. Close to the solution. He's working and the command is lowest. Lowest. And then
In the model type, what do I choose? GLS random effects?
no, fixed effect.
Okay.
Yeah, this is a special type of kernel. Lowest. No, but this is not the. So we are looking at some kind of adjustment, like a line, not a straight line, a line that synthesizes the relationship between logarithm of weight and education, for instance.
You can repeat the procedure. The procedure. First, we have to go to the statistics, then non-parametric analysis, and then we can choose the lowest significance.
So the way to do it is one way to do it is like Angel is doing. you go to not necessarily graphs, but also statistics, and also then go to the non-parametrics. So I was telling you non-parametric, lowest, go to the help. That was a good tip. Good tip. You have to go straight to the place where we want it. So this is the lowest smoother for this relationship, and I would like you to use also others like experience and other variables, so that you can see what type of relationship you may find. Notice that we are looking at pairwise relationships, only logarithm weights and one other variable. That is like the linear regression, simple linear regression. That is not telling you the whole story, it's just telling you part of the story, because we want to look at a multivariate model. And the multivariate model, relationships that look positive may turn negative, or the other way around. We don't know. We have to find out from the numerical properties of the data. So please do what Angel is doing there. Angel is just giving you some examples of how to get graphs that are informative for model selection and model building. Notice that this lowest smoother now comes through here. Depending on the resolution, you may find it here, but it certainly looks non-linear to me. Non-linear. It's like a curve. No?
Estamos haciendo two-way graphs. Two-way graphs. Y eso tiene una función, esa línea. Esa línea tiene una función.
Sí, lo que pasa es que no la sabemos, hay que estimar.
Pero lo arregla la finita.
Sí, sí. Faltaría, ¿no?
Sí. Mira, el gráfico,
Está aquí. Estadística.
no, el gráfico en sí no me sale. Me dice que me falta un pequeño... On the plot, X variable must be filled in. Está filled in.
Hello.
Está todo lo de OK y me dice X variable must be filled in. Pero es que está filled in. Educ. No, ya está en graphics.
Ahí estás en punto 09. Estás con una batería.
Mido graphics. No, pero graphics. No tuviera graphics.
Es que se puede hacer, o puedes directamente copiar el comando que te aparece ahí.
No quiero porque lo que quiero es dejar de aprenderlo. Si no, me voy a ver loco. Si voy a graphics, ¿por qué no lo consigo?
Porque posiblemente en gráficos sí.
Pero graphics es gráfico.
Análisis paramétrico. No siempre es acción, pero no sé, te parece que decir no paramétrico análisis. Mira, no paramétrico análisis.
Pero entonces estoy en gráficos.
No, este concretamente
o sea, el otro gráfico se hubiera podido hacer por ahí, pero es que tampoco, ¿no? El gráfico anual del lunes es smoother
Es que estás ya te digo, estás en versión distinta. O sea, estamos con esta versión que es 14 y esta es la 9.0. Entonces los menús cambian.
Pero es que claro, pero el gráfico básico no está desnudo,
Mira, pero ese
Okay,
es
so
lo
now,
que te digo.
what I would like you to look at is the output. The output that we have been looking at, the output of the fixed effect over the regression. And notice that that output has problems. If you want, you can save what you have been doing into the do
Pero yo no había
file.
hecho eso, había hecho esto.
Save everything that you have been doing into the do file so that you have a record of what you have been doing and you can start the next time from the end of the previous session and not from the beginning.
Bueno, vamos a borrar.
So,
Y a partir tengo que cerrar esto.
please, let's now look at the output. The output that we were looking at after you save everything to the new file. I would like you to go to the output and look at the results. So we can do it again. XTRay. Click twice, and if you click twice, it
Save.
executes.
Save graph.
Now, look at the output. The output that we have has problems because we have like 3 variables in which the computer is not able to estimate coefficient. So, and that may be problematic because we want a coefficient for black, we want a coefficient for Hispanic, we want a coefficient for education. But they are not there. They say they are omitted. So, do you have any idea why it's not there? Why it is omitted?
Because of collinearity.
Because of?
Collinearity.
Yeah, but I need more specific, no? Collinearity, what kind of collinearity? Why? Why does this happen?
But it says 0, doesn't say, it says 0 in the coefficient column.
Well, but it should not say 0 really because it just cannot do it.
Okay.
So it doesn't know whether this 0 is really not a good thing to write here. A little bar, a dot,
Here it
whatever,
says that.
but not a 0. No, coefficient 0 is not a good idea. It's not a good idea, and it's good that you pointed because I never really realized that it's not a good idea. So the problem is that there are some variables like these ones, like black. The variable black does not vary within each individual. No? Within each individual, the variable is always the same. Unless you are Julio Iglesias, no? Or Michael Jackson. No? Those people change from black to white or vice versa, but not the rest of the people don't. So the problem is that you don't have variation within each individual. This first estimator is called within, and it's only going to use the variation within each individual. There's no variation, so that's why it says 0, omitted, and it says because of collinearity, but the collinearity is due to the fact that that variable does not change within each individual. It has the same number.
Where did we select within? Because I did not.
Where you put dot FE, fixed effects. The fixtures. Okay, so now the Hispanic variable, what happens with the Hispanic variable? The same, not the same. This is like a race, it doesn't change a long time. And what happens with education?
Maybe it doesn't.
The fact is that it does not. Of course, this is one something that is peculiar to this data set, but this does not change within each individual. So we have, that is why we have that situation. Other things that we may want to look at is the coefficient, estimated coefficient, which is 0.065, 0.065, meaning that when the experience increases by 1 unit, by 1 year, then the wage increases by how much? 6.5 what? Percent. 6.5%. So 1 more year of experience means 6.5% more salary. That is the interpretation of that particular coefficient there. So the union, what is the interpretation of the union coefficient? When the union is a dummy variable, only takes 2 values, which is 0, non-union, 1, union. And then, what is the interpretation of 0.079?
If you are 1 part of the union, you earn 7.9% more than 0. That man who is not appointed in a union.
Yeah, okay, so that's the interpretation. No? And the rest of married, 0.064. What is the meaning of that?
Does it mean that if you marry, you earn 6.4 more?
Yeah, or if you are married. You marry or you are married.
Yeah, and I say it that way because everything else is constant.
Yeah, everything is constant. So that is the interpretation. So that makes sense or not? You think that married people are more productive, more reliable? It is the case that employers think that that's the case. So that is why they pay like 6% more to married people. If you are from the south, you'll earn like 11% more, and you work more hours, you make less money per hour. Less money per hour. And that is typical in this type of studies. Do you have any questions with this?
Yeah, why we have this problem with, for example, Black or Hispanic, because there is no variability within the individual, but what about being in a union or being in the South?
No.
There shouldn't be much of variability in those neither.
But in the union, people sometimes join a union, leave a union, typically because they change their employer, and they go to a firm in which there is no union.
Yeah.
They are not in the union anymore. It's just a matter of variability in the data. So, if you want, you can just do correlations and find out what is the behavior of the data. If you want, you can do like a tab, TAB, and of the variable union, and find out what is the situation here, what is the frequency, so you actually have a lot of information. You can do histograms also, so there are a lot of things that you can do, correlations.
So it varies enough to be estimated.
Yeah, it varies enough so that Stata does not complain. Okay, so now let's look also at the things that we were dealing with. F-tests. So there are like 2 F-tests. One F-test that you mentioned is in the output. Let's look at the output. And the output is, in the upper part of the output, you see F of 5, 3,810, and the p-value. F of 5, 3,810, and that is 172. 172, what is that testing? The F test. What is that testing? What is that test for? Eh? Yeah, that's the joint significance of all the explanatory variables, excluding the three that have been excluded. Okay? So, what is this telling us? Is it significant or insignificant? Eh? It is highly significant or a little significant? Highly. Eh? You look at the p-value, the p-value is very small. We don't know how small because we don't have enough zeros, but it is very small. So what this output is telling us is that the slopes are very significant, very significant. Y luego, here we have another f-test, the other f-test. The other f-test is this one that I was talking at the beginning of the video. This f-test down here. This is, what is it called? What is it for?
For fixed effect or less pool or less regression.
No. This is going to tell you about models, not estimation techniques. So no mixing models and estimation techniques. So models. Which models are we dealing with here? We are dealing with two models. The pool and the different constants. So that is what we are doing here. It's a test for homogeneity of the constant term, a test of homogeneity. And this is the previous test that I was telling you. 544. Why 544? Why not 7200? Then this is the number of what? So 544 is the number of individuals. It's 545.
Individuals or groups?
Yeah, the thing is that this technology allows for the use of groups, not only individuals. In this particular case, we only have individuals, so individuals and groups are the same. But in general, it could be groups.
And the number of observations is the number of groups, in this case individuals,
No,
times the number of variables.
No, it's the number of groups times the number of observations per group.
Because you have them several different times.
Because you have the same individual
Okay, within,
8 times.
that's the within variable. Okay. And the 5.3810 is what?
Where?
Right by the F? Right beside the F? No, further up, right by the F. The number you mentioned before. F, what is that number? Where does it come from?
This number is 5 is the number of slopes. 1, 2, 3, 4, 5. Not the constant. 1, 2, 3, 4, 5.
Okay.
And that is here. And then 3810 is the difference between this number of observations and number of groups plus 5.
Lo de la K y todo eso.
Sí. So this is the total number of observations minus the number of constants, which is 545, plus 5.
And the probability of being superior to F is 0, which means it is highly significant. But I guess
Well, the idea is
because it's comparing the
we,
actual F.
we have computed an F, which is 172. And one wants to know whether that is big or small.
Yeah.
And the idea is, you look here at the p-value. The p-value is the probability of observing a value of F bigger than 172 just by coincidence. So the probability of coincidence Very small.
But with a significant, at 0.01 or at 0.05 at some level, because otherwise it could not be zero.
Yeah, but the idea is that the probability, this probability has to be smaller than 0.01.
01, exactly.
0.01.
Ah, I didn't know. Yes.
So here, if we go back to this here, to the heterogeneity, what do? We reject the null of homogeneity, or we do not reject the null of homogeneity? We reject. No? Now, if we reject the null of homogeneity, what do we have to do? We have to use constant, one constant, several constants, one for each individual. No? That is what we are testing, one for each individual. Okay, so now, do you have more questions about the output? You see that the output is telling you that we have, on average, 8 observations per individual, a mean of 8, a maximum of 8, a minimum of 8, so everything 8. Do you have any questions about the output? Anything weird that you may want to look at? Well, now we have seen that this technique does not allow to estimate the coefficients of 3 variables which are important. So let's look at other techniques that will help us to estimate those coefficients better. One is another very simple estimation technique for the same model that is called between. So we have the same model, different estimation techniques. First, we have used OLS. Second, we are going to use another different technique, which is called between. So you put a B instead of an F, and then we have, magically, we have another estimation.
¿Me has puesto el comando ahí abajo? Yo no lo tengo. Es que yo no tengo.
Sí.
Yo no tengo todo eso que pone ahí.
Esa es la versión 9.
Es que no he perdido una clase, tengo la versión que no es. Estoy aquí, no estoy.
No, está bien.
Pero no tengo escrito lo de abajo.
¿Eh?
No tengo escrito lo de abajo para poder pasar.
Sí, es que una vez que lo ejecutas, ya desaparece.
¿Y cómo lo has hecho?
Magia.
Sí, vamos.
No, lo tenías ahí, lo tenías todo. Lo que pasa es que tiene, si esto lo abres, lo ves todo mejor.
O sea que tú has pinchado en otra opción.
Claro.
Porque antes estamos ahora en between, estábamos antes
En fixed. So now we are in between. Between, we are using only the variability between different individuals. So we are just discarding the variability within individuals. No problem then with the possibility of one individual not changing the race or the color or education, no problem with that. Because now we are looking at the variation only across individuals. And that is the case of this particular output here, in which you see that we have estimations for the parameters that we could not be estimated in the previous way. So look at the black. Black, how do we interpret the coefficient of black?
You don't become black, you simply are black.
If you are black. If you are black, how much more you make?
12%
Less. 12% less. But in experience, if you have one more year of experience, how much more do you make? 2.7%. So this may look small, but you can get 10 years of experience, 20 years of experience, so it becomes accumulated. And then Hispanic, you make a little more. You make a little more. Although the Hispanic is insignificant, if you see here. So you have to be careful not to interpret coefficients that are insignificant, because typically you put yourself into trouble. No? Education is about the same as typically the education has a return of 9%, so that it happens in all the studies. And see here, this is like 8.99, so almost 9%. The union here is, I think it's overrated. It says 25%. Maybe this is just a simple estimator. Married 15%. So there are some other things to say, but if you see, this has the ability of estimating some parameters better than in the previous case, and this looks good.
And some worse, I would say.
And some worse, of course.
Because
yes.
experience is better to compare within, I would say.
Yes. But you see, now we have like two sources of variation. One within each individual. That was the previous thing. And this is only the variation between individuals. So we are looking like a schizophrenic. No? Only one, only the other. So the idea is now to try to combine the two sources of variation into just one estimation technique, and that will be the generalized least squares, which is called RE, random effects. The RE is a different estimation technique, and this different estimation technique is useful for estimating, as you see, all the parameters. And what this does is to optimally combine the variation between and within. So it is a more sophisticated way of estimating, which is called generalized least squares. So the model is essentially the same, but the estimation technique is different. And it is called generalized least squares.
Yo no tengo A y lo edito, es más.
Sí, lo pones, lo editas al pones. Cambias el B.
Pero si pincho no lo puedo editar con gráfica, ¿entiendes? Lo tengo escrito, si pincho aquí me lo va a dar. Aquí yo tengo todo esto igual, pero pone, en lugar de A y pone I y ¿cómo digo eso? Lo único que edito es que
So now, what I would like you to do is look at the output, see what is weird there, see that you have differences from the previous estimation technique. Notice that now we don't have an F test. We have a walled chi-square test. And that means that since we are not dealing in the very simple situation of OLS, then we have to use approximations. And the approximation is now based on the generalized least squares. And that means that the joint test for significance is not as easy as before. It's not an F test, but it's rather an approximation which is called wall test. The wall test is, I don't know if you have heard about wall test or not. No, it looks that you don't. The wall test is essentially estimating a model with under the alternative hypothesis and then checking for the null. And it is a very common way of constructing tests. Wall tests are very common. The t-test and the f-test are subsets of examples of wall test. Wall is a strategy for constructing tests. And you may or may not have heard about this, but there is a triad of tests which is called, one is wall, estimating under H1, then Lagrange multipliers, estimating under H0, and then the likelihood ratio. And that is estimating under H0 and H1. So this is like the threesome of tests: Lagrange multipliers, wall, and likelihood ratio. Sometimes this is called LM, and this is called LR. So I don't know if you have heard about any of these or not, but they are common. If you look at in Google and look at all of these, you will find a good description. Google in English. You will find a good description of all these and what is the relationship between these. But many of the tests that you already know belong to one of these three categories. Typically, tests based on the residuals are Lagrange multiplier tests. The white test of heteroscedasticity, or the Breusch-Godfrey of serial correlation. All these are Lagrange multiplier tests. And some other tests, like the t-test or the f-test, are wall tests. We don't have enough time in this course to go over this on detail, but I wrote my dissertation many years ago about this, so these tests are very close to my heart, but we don't have time to go over this on detail.
So, I don't understand what do you mean when you say under hypothesis 0 or alpha?
Yeah, the idea here is assume that you have to test for heteroscedasticity. Okay, so you would use the white test, for instance. How do you actually implement the test? What you do is you estimate assuming homoscedasticity or OLS, and then check the square of the residuals for heteroscedasticity. That would be a estimating under the null, and then checking for departures from the null. That would be a Lagrange multiplier test of heteroscedasticity. So that is the idea. A wall test would be different, would be estimate assuming heteroscedasticity and then check for the possibility of homoscedasticity. So those are different strategies for testing for testing hypothesis. Maybe a statistical hypothesis or maybe economic hypothesis. Do you have any questions? So here you have another estimation technique. It's different. I was saying that this is a chi-square test. The idea is with 8 degrees of freedom. So the idea is that you're checking whether all the coefficients are significantly different from 0 jointly. So you're checking about these, all of them except the constant becoming 0. Are they all of them 0 at the same time? That's a question. That's null hypothesis would be each one of those is equal to 0. Null hypothesis would be that. The alternative hypothesis would be that some of them or all of them are different from zero. So this test is telling you whether all of them are significant or not. 981, is that big or small?
Big.
Big, no? It's big. It looks big because it's many numbers, but what you really want to look at is the probability to the right. The probability to the right. How likely is it to get a value just by chance that is bigger than 968? And it is very unlikely. It's 0, 0, 0. We don't know if there are more zeros here or not, but it is unlikely. Do you have any questions? Any questions?
But so that tells you that all of them together are significant.
Yeah.
Suppose all of them are very significant, but one is not at all.
Well, that's the
that
case
will not
here.
work out.
It is the case. Here, this one is not significant, this one is not significant.
Okay,
This
so
is
it's
like looking at everybody's, is the rest of, is the whole of us rich or not? Well, maybe we are jointly rich, but then Paco is very, very poor. It may be. So that's the
Because
case
it's not
here.
telling you that they're all significant. It's telling you
Yeah,
that
it's
the
telling
group
you that
together
the
is
group
significant.
is significant. But there's no contradiction in this. There's no contradiction. So if you think there is a contradiction, there's a problem. No contradiction.
No.
No. Then what one would do is typically would delete these two variables from the regression and then run again. So let's do that again. Let's delete these two. Yeah. And Hispanics also. So now, if you delete these two variables, what we get is that all of those who have been left are still significant, and the chi-squared 6 is now 968. How much was it before? More or
According to my
less?
screen, slightly less, very, very slightly.
But less now or before?
Before less.
The idea then is that now they are all jointly significant and individually significant. So this is what we want, jointly and individually significant. And do you have any questions, any other things that you may want to look at here?
How do you derivate R square within between and overall?
Well, the idea is that you want to measure the R square in some way. The R square is 1 minus sum square residuals over total sum squares. So this is the R square. Now, typically we only have one R square, which is the joint, the overall R square. But here we have different dimensions. You can measure the R square depending on how you measure the total sum squares in the individual dimension or in the time dimension. And that is why we have this. We have, you remember the within estimator? The within is the fixed effect. And that corresponds here. This is the R square of the within estimator. This is the R square of the between estimator that we already looked at. And this is the overall. The overall is this one.
Wouldn't this mean that the between does not add much value? Because the within is more powerful than the overall. Well, a bigger
No,
house,
but that is not the only thing that one wants to look at. One wants to look at not only the fit of the model, but also the efficiency of the model. And we need a model that is very efficient. And the efficiency here typically is larger in the random effects estimation with generalization squared than in the other cases. So the fit, the efficiency, are
What is the efficiency?
efficiency is the variance of the estimator. So we want to have estimators that have minimum variance. And that is what we get with the random effects GLS. Do you have any questions? Any questions on this? So now we have looked a little bit.
Sorry, can I ask about the sigmas at the bottom?
No.
Okay.
No, because I don't want to get into that. Because I want to see that in the theory first. Because if you ask me, I cannot say anything. But if we look at it in the theory, and you will see what it is. Entonces vamos al tema. So if we don't have any more questions about the basic handling of the data, at least save everything. Save everything that we have done.
¿Cómo se save?
And make the comments. Make the comments because a few days from now you will forget totally about everything that we are doing.
Are we gonna save now? Are we gonna save the file?
Yes, save everything. Save everything. Si vas a archivo, ¿verdad?
Let's do again for the procedure. You have to open the.
Data editor.
No, it's for them.
Ah.
I'm at file, what is
Do
this?
file.
But I don't have do file. I just have do.
That's it.
Do.
Okay, so now save everything that you have,
Y entonces
and then we go back to the lesson number 3. Lesson number 3 is the lesson in which we are going to see all these estimators
This is the
in more detail with the theory.
No, yo le he dado file, le he dado file.
Properties.
Pero aquí no vale tampoco.
No, aquí. Mira, file, file. Y lo que haces es.
Lo puedo seleccionar.
Lo vas a incluir en mira, vamos a escoger los comandos que quieren guardar en el file.
Qué complicado.
Este se perdió, pero no te puedo compartir lo que hemos hecho.
Si para el próximo día no lo voy a tener.
No, por eso te puedo compartir lo que hemos hecho.
No voy a compartir.
La
Te voy a
fila.
enviar.
Te lo voy a enviar.
Ah, pero no me iba, vale.
No, lo voy a poner en la carta.
Ah, no.
Mira, se ha cerrado porque no da más de sí.
Ah, vaya, vaya.
Se bloquea el ordenador. Sí.
Adiós, sí, me he ido del todo.
So remember to write the comments. Write the comments always with a star in the beginning of the line. Star at the beginning of the line, and then a comment. If you need to use several lines, just go ahead and use it. Okay, so now lesson 3 is about heterogeneity. How to deal with heterogeneity. There are several different ways of dealing with heterogeneity. and we are going to study here a few simple ways to deal with heterogeneity in panel data. The first one is using different constants for different individuals. Typically, it will be one constant for different individuals. The idea is that you allow for differences in the means of the independent variable without necessarily having differences in the means of the independent variable. So let's and the idea of using different constants for different individuals is that it can capture this simple way of dealing with heterogeneity, can capture the idea of variables that vary across individuals but not across time, or even variables that vary across time but not across individuals. So typically, I would like you to think of an example. The example would be, assuming that we are looking, for instance, at a wage panel. A wage panel typically tells us that the differences in wages are due to individual characteristics or individual things that are observable. But if you think carefully, you will see that the most important thing for difference in the salary is the ability or the how hard a person tries. Ability is something that is unobservable, and it is changes across individuals, but typically does not change within one individual, and it's very well captured by the constants that are different for each individual. And that is the idea that we have here. So typically, it is also important for numerous omitted variables that vary across time, that are individually unimportant but collectively important. So essentially, what we are dealing is the heterogeneity, unobserved heterogeneity now is treated using constants, different constants, and the constants are capturing omitted variables. That is very important. Omitted variables, so let's continue, that vary or not vary across time. How do we do this? We do it with a fixed effect model. It is called also OLS with dummy variables, but please do not mix model with estimation technique. So it is a model that can be estimated by OLS, but it is a model essentially a dummy variable for each individual. It's a simple model, it's a useful model, and it's what we call typically the fixed effect. It is typically estimated by OLS. Typically estimated by OLS. It is a constant dummy for each individual, OLS, and it is blue. Blue means best linear unbiased estimator. So what it does, this is telling us is that the assumptions for the Gauss-Markov theorem hold. Assumptions for Gauss-Markov are essentially that the model is well specified, that the data is behaving well, that the errors don't present problems, no correlation, no heteroscedasticity, and that allows us to say that the ordinary least squares estimator is efficient. Efficient, but not is the best in the world, it's just efficient within the class of estimators that are linear and unbiased. So this is the Gauss-Markov theorem. We are not going to go into detail with this because this is something that belongs to previous courses. There's no theory more than you already have. It is as simple as it looks, and it's saying that ordinary least squares is best linear unbiased, and that's it. It is important to know this because the fixed effect model estimated by OLS is used very heavily in panel data analysis. So it is used very heavily because of these properties, very important properties. How do we actually estimate? If we had to do it by hand, the estimator would be this one. This is beta hat of covariance. The upper part is just the estimation of the slope coefficients. Those slope coefficients are estimated in a very simple way using ordinary least squares. In theory, if you would have to do it by hand, that would be the expression. And the expression, you can read it easily. It is like x prime x to the minus 1, x prime y. It is the same. No? If you take your glasses off and you don't look at the details, it's x prime x to the minus 1, x prime y. The only thing is that now we have subtracted the average from everything. We have subtracted the average from everything. And the reason why we have done that is to be able to estimate this more simply. No? You may or may not remember that you can estimate a model in deviations from the mean, you remember. And the estimation is the same. Estimation of the slope coefficients is the same. So this would be the idea. If you look at more in detail, you put your glasses back on, then you will see that first we sum the variation of the individual within each individual. Within, it's called within. First, the variation within each individual from t equal 1 to t capital T, one individual, and then you sum for all the individuals from I equals to 1 to n. So this is the variation that we have in decomposed. First individual and then sum over individuals. That would be the simple idea behind this estimator. CV is called covariance because this estimator can be derived from different ways and interpretations of statistics. Many. It's not only OLS. It can be interpreted from many ways. And this would be the typical slope estimation of a model estimated in differences from the mean. You know that the coefficients are the same and they can be interpreted the same. There's no change. X prime x to the minus 1, x prime y. That is the way to, I'm sure that reminds you of the OLS estimate. And then you say, well, we are estimating the slopes. The slopes are a few, 5, 8 we have seen in the example. But how about the constants? Well, the constants are estimated in a very simple way also, which is just the forecast of the y minus the so this is the y bar, which is the average of the y, and then the slopes times the average of the x's. So this is exactly the same as how to recover the constant from a regression that was estimated in differences. You may remember or not, but it's this way, exactly the same thing. Except that now we have many of those. We have capital N of those. So this, of course, you don't need to remind this, but you need to know that this is what Stata does. Stata does this for you. So you get all the results and you don't have to do anything by hand. Then, so I'll finish with this. I just want to introduce a matrix that we are going to mention but not use very heavily. A matrix that is very simple, that is the Q matrix. The Q matrix is designed to just take the average out of a given vector. That is the whole point, no other point than this. And that is what it does. It takes the average out. Of course, since we have been looking at the previous formula in which we had to take the average of each variable, then the Q matrix is apparent and is designed to do this. Why do we use the Q matrix? Because it is more compact than the other notation, and because you can operate with the Q matrix easily. You can multiply the Q matrix times itself, and so you can do a lot of things with the Q matrix, which is also a symmetric matrix. So it eliminates individual effects. That is the point with that matrix. Do you have any questions? Okay, so I guess this is time to stop, and we'll continue next Wednesday. Yeah? Next Wednesday is what day? 10. 10. Okay, so we'll continue on 10 because when don't we have class? On the 24th, I think. Okay, so 10 and 17 we have class. In the next class, I will continue with lesson 3, and we're going to finish completely lesson 3, and then we go next to lesson 4, and then make practice after lesson 4. So for now we are not doing more practice than what we have been doing today. Next class is lesson 3, complete. No practice.
Este que te preguntar al final, pero
Muchas gracias.